Hello everyone. So today's topic is thermodynamics. So unfortunately, I couldn't do the previous webinar, so very sorry for that. I don't think we have time. I ran out of time to do it because unfortunately I wasn't available. Um, I wasn't available last week. Anyways, thermodynamics. Thermodynamics is study of heat processes. Basically, it's an flow of it's gases doing work and well, gases being heated. So something that was studied heavily in the 18th and 19th century during the Industrial Revolution with the invention of the steam engine. And of course, people wanted to know how much coal they need in order to create, I don't know, whatever they were creating at that time. So if you want to make, if you want a machine to work, you want to know how much coal you need, what the temperature is, etc., etc., etc. So and then that was the period where they dis discovered, well, thermodynamics discovered. They didn't discover thermodynamics, of course, but the this thermodynamics appeared, and it's cool. Which in the A-level course, you don't really do thermodynamics because you don't do the laws of thermodynamics. You just do ideal gases. Here, I will try to remedy that. So, to tell you about the first law of thermodynamics. We will be touching one of my favorite laws of physics, the second law of thermodynamics. But the first law of thermodynamics goes like this. So imagine you have a piston and so a cylinder with a piston. And inside you have gas. So first law of thermodynamics. Dynamics. If you supply heat to the gas, heat Q, then the molecules will move faster. They will hit this piston, and the piston will move into a new position. But because the piston has moved, that means work has been done because the gas applies a force on the piston. So force on piston, and the piston moves. That means gas does work on the piston. And this we'll label this as W. W is the work done by gas. Also, the gas has internal energy. Gas has internal energy. Internal energy, which is, we label it U. Internal energy, U. So it's the sum of the kinetic and potential energies of all the particles. It's the sum of kinetic energy and potential energy of all particles. Do you have any questions so far? Please ask. Is everything clear so far? Okay. Right. So when the gas does work, it can use the heat supplied, or it can use its internal energy. Right. Okay. So the first law of thermodynamics goes as follows. The heat supplied to the gas can be used either to increase the internal energy of the gas, or make the gas do work. Or in other words, uh, yeah, that's the gas do work. Work done by gas. Gas. That's one way of writing it. Once again, you supply heat to the gas, and the gas can do two things. Get hotter, that means the energy goes into U. So if U increases, if delta U is greater than 0, gas gets hotter. Hotter. Or if W is greater than 0, gas does work. Work. So you can do either, right? You give the idea is you give energy to the gas, and the gas can do one of two things. It could get hotter, or it can do some work. Go. There's another way of looking at the first law of thermodynamics. It is like this. Rather than gas doing work, you can do work on the gas. Basically, you can take some gas and you can squeeze it. In this way of writing the first law of thermodynamics, which is the same law, of course, uh, to change the energy of the gas, you can supply heat, or you can do work on gas. So the equation is not the same because the work done by the gas is minus the work done on the gas. I mean, it's kind of obvious. If the gas does 7 joules of work, it's the same as doing negative 7 joules of work on the gas. I hope that makes sense. So yeah, so this is another way of writing it, and it also makes sense. So imagine your hands are cold. What do you do to make your hands warm? Well, you can rub them. You can do work. If you rub your hands, they get really warm. Okay? That's one way of heating your hands. What's the other way of heating your hands? Well, you can put them on a heater. Yes, if you place your hands against a heater, you increase the internal energy of your hands. So delta U is the energy of your hands. Or you can rub your hands on the heater, and that means even more. You get heat supplied, and you do work on your hands, and this way you increase the internal energy. So this is the first law of thermodynamics, and for some reason it's not studied in most A-level courses, but yes. So, and I think it's a, I think I think it's a pity. Let's put it that way. Okay, so let's jump to problem 1. A steel sphere of mass 2 kilograms falls freely from a height of 15 meters. So you have a height of 15 meters, and it falls and hits the ground. And as a result, because it hits the ground does work to stop the sphere. Ground does work to stop sphere. And that means this work goes into internal energy. This work goes into increasing internal energy. In other words, delta U, the change in internal energy, is equal to the work done. And the work done is obviously equal to the kinetic energy. And the kinetic energy is equal, when at the point of impact, is equal to the gravitational potential energy. So in other words, this is a fancy way of saying that gravitational potential energy is converted into internal energy. And we know that for a steel sphere, the change in internal energy is Cm delta T. and the gravitational potential energy is mgh. So mgh is Cm delta T. Mass of the sphere can be cancelled, and the change in temperature is gh divided by C. And we can look up the value for C for steel, specific heat capacity, to steel. 420 to 500. Let's take middle value. 460. Okay. So that's equal to G, which is 10 newtons per kilogram, multiplied by H, which is 15 meters, divided by C, which is 460 joules per kilogram per Kelvin. And therefore, Newton times meter is a joule. So Newton meter and joule cancels. Kilogram cancels, and you get 1 over Kelvin. So that's 150 over 460 Kelvin, which is 150 over 460, 0.33 Kelvin. 3 Kelvin, or 0.33, which is 0.33 Celsius. The change in temperature is always the same in Kelvin and in Celsius. It's weird to say that 0.33 Kelvin is the same as 0.33 Celsius, because it's not really, but yeah. Anyways, each breath taken by a person exchanges approximately 0.4 liters of air with the surroundings. Estimate how many molecules from historical figures final breath, usually it's Julius Caesar, mixed uniformly with the atmosphere are inhaled in a single breath today. So there are many different ways of how to approach this problem. I will go with the mass, because first I want to talk about how would you estimate the mass of the atmosphere? Okay. So I'm going to find the mass of air in one breath. Mass of air in one breath. So what do I know? Mass of air in one breath. Well, mass of air in one breath is the density of air times the volume. And the density times volume is very simple. Density of air is approximately density of air 1.3 kilograms per cubic meter multiplied by the volume. And the volume is 0.4 times 10 to the negative 3 meters cubed. Right, so meters cubed cancel, and you get 1.3 times 4, 5.2. 5.2 times 10 to the negative 3 kilograms. So that's approximately 5.2 grams. 5.2 grams of air. Okay, every breath. Now, I want to know the mass of the atmosphere, right? Mass of atmosphere. Atmosphere. This is a very common question on university interviews. I don't know if you've done yours. Have you done your university interview? Or is it something you are looking forward to? Let me know in the chat. No. Okay. Mass of the atmosphere is it can be found in many different ways. My favorite way is as follows: and it's so easy that like a year 8 student can do it. Honestly, mass of the atmosphere. So imagine the whole Earth, right? And the atmosphere pushes on the Earth, right? atmosphere pushes on top. So the pressure is equal to the force divided by the area. But isn't the force just the weight of the atmosphere? Because what's pushing on the Earth? Well, it's the weight of the air. So that's the weight of air divided by the area. So all we need to do is find the area of the Earth. And we know that the radius of the Earth is 6,400 kilometers. And the area of a sphere is 4 pi r squared. 4 pi r squared, which is 4 pi multiplied by 6,400 6,000 squared meters, because we want the answer in meters. And so we can get the area of the planet Earth, which is 4 pi multiplied by 6 squared, 5.1 times 10 to the 14 square meters. Square meters. And so the weight of air is the area multiplied by the pressure. And we know that the pressure is 10 to the 5 pascals. Atmospheric pressure is 10 to the 5 pascals. In area, we know, so it's 5.1 times 10 to the 19 newtons. And the mass is the weight divided by g, of course. So that's 5.1 times 10 to the 18 kilograms. So do you fully understand how I found the mass of the atmosphere? And you can see it's so easy. Like when you ask, what's the mass of the atmosphere? And it's so easy to calculate. I don't know. Do you appreciate that? Do you like this? Did you know this before? Did you know how to do this before? So we can see that. Oh well. We can easily find how many breaths it takes for the whole atmosphere. Now we want to know the amount of molecules in one breath, number of molecules in one breath. Number of molecules in one breath. So we know that one breath is 5.2. So we want to know the mass of the one molecule. So the N is going to be mass of air divided by mass of one molecule. Air, the molar mass of air, is 29 grams per mole. And we know that 1 mole is N Avogadro. So is N Avogadro molecules. And that means that's 6.02 times 10 to the 23 molecules. So mass of one molecule is 29 grams divided by 6.02 times 10 to the 23, which is 29 divided by 6.02, that's 10 to the 23, 4.8 times 10 to the negative 23 grams Okay. And we can do 5.1 gram divided by 4.8 times 10 to the negative 23 grams. Grams cancel. And so 5.1 divided by answer, which is 1, or 10 to the 23. So approximately 10 to the 3 molecules. Okay. 10 to the 23 molecules. That's in one breath. And per if you take 10 to the 23 molecules and you spread it around all the atmosphere, so you want to know um, in every breath, in every breath you take, there are, so 10 to the 23 molecules, yes, but the proportion of the molecules, so you need the 10 to the 23 multiplied by the mass of air in one breath, so it's 5.1 grams, divided by 5.2 grams. That's okay. I kind of made a mistake here, but 5.2 doesn't really make a difference. 5.2 divided by 5.1 times 10 to the 18 kilograms. So this is 5 to the 21 grams. 21 grams. And so this is 10 to the minus 21. So this cancels. It's 100. 100 molecules from Caesar's last breath. Okay. Is that result surprising to you? So Julius Caesar is the one that died 2,000 years ago. Slightly surprising. Okay. Well, you know that when you breathe out carbon dioxide, right? You breathe out carbon dioxide. Um, Now trees use carbon dioxide to grow. So, for example, I have a almost dead tree here, but hopefully it will survive. Um, and it absorbs carbon dioxide. And if you think of the tree trunk, it's made of carbon, right? And where does the carbon come from? Well, it comes from carbon dioxide. And some of that carbon dioxide is the carbon dioxide you breathe out. And the tree absorbs that carbon dioxide, spits out oxygen, which it doesn't need. It needs because it needs the carbon. So it grows from the carbon. And in every breath you take, well, you know, where there are about 10 to the 23 molecules, about 1% is carbon dioxide. So there are 10 to the 21 molecules of carbon dioxide. Now there are about 10 trillion trees in the world, so that's 10 to the 13 power. So for every tree in the world, in every breath you spit out, there's about 10 million, 100 million molecules of carbon. So because you've been breathing for quite a while, you can safely say that every living tree in the world contains carbon produced by you, which is quite cool to think about. So yeah. All right, so let's move on. A hot air balloon, a spherical hot air balloon, has a radius 12 meters and carries a total load of 150 kilograms. The surrounding air is at a temperature of 290. Determine the minimum temperature of the air inside the balloon to require for it to be buoyant. Okay, so hot air balloons. A hot air balloon will fly if the total mass of the hot air balloon is less than the air that it is displaces. Okay, so balloon flies, floats if it weighs less than the air it displaces. But it has air inside. It has air inside, but the air inside weighs less than the air outside because it's hot. So when you heat up the air inside the balloon, what happens is some of that air comes out from the bottom hole. And so the density of the air inside is less. So mass of the air inside is, well, mm, okay, mass of displaced air. Let's start easy. Just air is density of the air, of the cold air, multiplied by density of the cold air, multiplied by the volume of the balloon. Mass of air inside is density of the hot air multiplied by the volume, and mass of the basket, etc. Basket plus people is 150 kilograms. Let's just call that M. So we want density of the cold air times V must equal to the density of the hot air times V plus M. And that's the minimum. That's the minimum, yeah. Okay. Now, let's write down the gas law. Ideal gas law. Ideal gas law. So PV equals nRT. The number of moles. But the number of moles can be written as the mass of the gas divided by the molar mass. Mass divided by molar mass. And so we can write PV equals M divided by mu RT. And if I want density, to find density, I need mass divided by volume. So I divide both sides by volume and multiply by mu. So P mu equals M over V RT. And this is density. This is density. So density is P mu divided by RT. Okay. So you can see the density is inversely proportional to the temperature because the pressure is fixed. Pressure is equal to the pressure of the atmosphere. Like it has an opening. The pressure inside is equal to the pressure outside because it has to be. It can't be otherwise. Because it has an opening at the bottom. So density of air inside and density of the inside. Okay, so we can rewrite that equation as pressure mu divided by R T outside times V rho V equals P mu divided by RT inside times V plus M. And from here, what do we need to find? We need to find the temperature inside. Okay, so we have P mu divided by RT out times V minus M and multiplied, equals P mu divided by RT in. T inside is equal to P mu divided by R multiplied by P mu RT outside times V minus M. Okay, and then we just substitute. Well, we don't, we can simplify, hopefully. Do we want to do that though? Yeah, we could. We can do P mu like this. So 1 over R over P mu. So it's going to be open bracket 1 over T out times V minus mr over P mu. And this is just V. Okay, I think we don't need to go any further than that in simplification. So 1 over volume 4 pi times 12 cubed. Oh, word, sorry. 4/3 pi times 12 cubed divided by T out is 290 Kelvin. Okay. Minus M minus 150. So gas constant is 8.31. Pressure, we assume atmospheric pressure. And mu is 0.029. That's the molar mass of air. So that's kilograms per mole. Kilograms per mole. I won't bother with the other units. So apologies. I'm kind of cheating here, but I'm doing everything in an SI, and that's the beauty of SI systems. So you don't have to worry about conversions. Times 8.31 divided by 100,000 times 0.029, and then 290. Hopefully I get something. 4 divided by 3 multiplied by pi multiplied by 12 cubed. I get nonsense. I went wrong somewhere. Um, molar mass. So density is directly proportional to pressure. mu RT. That makes sense. Okay, I forgot volume here. And that means T in PM mu V. So that's 1 over V. And then you have V here. How could I have done this? It's such a silly mistake. Okay. One over 290 mR times volume times 4 divided by 3 divided by 12 cubed. Three hundred and 307 degrees. 307 Kelvin. Oh yeah. So you only need temperature to go up by 27 degrees. Oh, which is nice. Okay. There's Kelvin. Okay, that's good. A vertical cylinder contains an ideal monatomic gas beneath a frictionless piston of radius 8 centimeters. The gas initially occupies a height of 25 centimeters at room temperature. A mass of 12 kilograms is placed on the piston, and the heat is added until the piston rises by 4 centimeters. Assuming no heat loss and no external atmospheric pressure, calculate the heat supplied to the gas. So we have a piston. I'm kind of worried about the monatomic. Why would we need monatomic here? But let's see. Um, okay, so we have a piston, and radius is 8 centimeters. The height is 25 centimeters at room temperature. So we can assume room temperature is 20 degrees Celsius, which is 293 Kelvin. A mass 12 kilograms. So we place a mass, which is 12 kilograms, on the piston. So, well, the thing is, when 12 kilograms is placed on the piston will go down. Um, the question is not it's not very obvious what happens. So, are we releasing? Because if we let go, if you place 12 kilograms on a piston, it will move down. Then if you add heat, obviously it will rise. But does it rise from the new position, or it rises 12 from the original position? Well, let's try to solve this in two sections. So first, we place the 12 kilograms, and the piston slowly moves down, slowly, and in fact, allowing the temperature to not to increase. basically leaving enough time for the temperature to settle. Yeah, to settle. Okay. So what's happening here? We have when it lowers, work is done on the gas, and it's a bit more tricky than I thought. Just a second. You place the mass piston moves down. What happens to the energy? What happens? No, the gravitational energy goes into the system. I think we need to make a few more assumptions. No, we place the mass and we hold it. We hold it in place, and we heat the gas until it starts rising. So basically, we uh, we don't allow the mass to go down. So assumption. We do not allow the piston to fall because that's problematic. That makes the problem so much harder. We don't allow the piston to fall. So we hold the mass until there's enough pressure, for the gas to actually rise it. Okay. So when piston is so initially, the pressure of the gas, because it's a light piston, frictionless piston, frictionless, massless piston. Initially, pressure of the gas is equal to the pressure of the atmosphere. So basically, the piston just closes the lid, but there's no pressure, no additional pressure. When 12 kilograms is placed on top, the new pressure is pressure of the atmosphere plus the weight of the piston, so mass G divided by the area, so pi r squared. Right. Now, what happens next is that you're adding heat at constant pressure, because now the pressure is determined by the mass on top of the piston. Heat is added at constant pressure. And therefore, heat is added at constant pressure, and the amount of heat that is added is going to be the number of moles times Cp and times delta T, where Cp is the heat capacity of a gas at constant pressure. And because it's a monoatomic gas, for a monoatomic gas, Cp is 5/2 R, which is approximately 20.8 joules per mole Kelvin. Right. Well, so we want to know the final temperature of the gas. So initial volume V1 is equal to pi R squared times H, which is I times 8 squared U times 0.08 squared times 0.25 5 times 10 to the negative 3 cubic meters. Final volume V2 is going to be pi R squared times H2, which is pi times 0.08 squared times 0.29, because it rises by 4 centimeters. So times 29 divided by 25. So it's 5.83 times 10 to the minus 3, 0.03 meters cubed. All right, so initial temperature is, we know that, the gas law. So PV equals nRT, and initial P1 multiplied by V1 equals the number of moles of the gas times R times the temperature, and the temperature is room temperature, T1. So we can find the number of moles of the gas is P1 V1 divided by R T1, which is 10 to the 5 times the volume, 5.03 times 10 to the negative 3, divided by R, so 8.31 times T1, which is hmm, just a second. Okay, well, the number of moles, and let's see if we get a decent answer, times 5.03 times 10 to the minus 3 divided by 8.31 divided by 293. Something is wrong, something is off. 5.23 times 10 to the minus 3. Okay. Yes. All right. My first solution was wrong. Okay. Anyways. Yes. So this is times the temperature 293. So that is 0.21 mole. This is the amount of gas inside the piston. That's yes. And then you heat up the gas, and the final temperature P2 V2 equals nRT2. Now it is a new pressure, so we want to have T2 is equal to P2 V2 divided by nR, and this is going to be P2. So the new pressure is well, let's add this. So it's going to be 10 to the 5 plus mg, so which is 12 times 10 divided by 3.14 times 0.08 squared, which is 100,000 plus 120 divided by 3.14 divided by 0.08 squared. So it's going to be 1.06 times 10 to the 5 pascals. So the pressure has increased. So 1.06 times 10 to the 5 times volume. The new volume is 5.83 times 10 to the minus 3 divided by n, which is 0.21 times 8.31. So that's the new temperature, 1.06 times 10 to the 5 times 5.83 times 10 to the negative 3 divided by 0.21 divided by 8.31, and that is 354 Kelvin. Oh, so quite a significant temperature increase. So the temperature has to increase by about 60 something Kelvin. And now we finally get to use the heat added. So the amount of heat added is the N, number of moles, times Cp times delta T. So that's going to be 0.21 times Cp, which is 20.8, times the change in temperature, which is 354 minus 293. And that is 0.21 times 20.8 times 354 minus 293, which is 266 joules. Lovely. Okay. Okay. Not too bad. Okay. An ideal gas undergoes adiabatic expansion from Va to Vb. The initial pressure and temperature are Pa and Ta. Calculate the work done by the gas during this expansion and relate it to the change in internal energy. Okay, so an adiabatic expansion is a process where no heat is exchanged. Adiabatic means that Q is 0. So we can write Newton first law of thermodynamics. And this goes like this. Work done by the gas. So the heat supplied to the gas is equal to the change in internal energy of the gas plus the work done by the gas. But because this is 0, that means that the change in internal energy is equal to minus the work done by the gas. Okay, so now I think we would benefit from a diagram. So adiabatic expansion from volume VA. So this is P, this is V, and it's an expansion. So we go from VA to 2VA. So the process looks like this. Not a fan. Let's make it more interesting. So VA to VA. And it goes like this. So A, B. So it's an adiabatic expansion. So this is PA and PB. Calculate the work done by the gas. Well, the work done is equal to the work done is the area. Work done is the area. Okay. If we approximate it with a straight line, we could find. Obviously, it's not a straight line, but the work done, because for an adiabatic process, PV to the power gamma is a constant. Or in other words, PA VA to the power gamma is equal to PB times VB to the power gamma. For a monatomic gas, a monatomic gas, gamma is 5/3. Gamma is the ratio of CP to CV. Okay. Right. So now we can in any adiabatic process. So sorry, I messed up the scales. PV, of course. What am I doing? I'm just being very silly at the moment. It's the other way around. The axes are completely wrong. Okay. So P, of course, and this is V. And you start with VA and VB. So yes, the area to the graph. And this is PA. And this is PB. So the pressure decreases, of course. What am I doing? So yes, pressure decreases and the volume increases. Pressure decrease, volume increases, and the work done is the area, and this is obviously the integral from VA to VB of P of V. So it's a function P of V dV, and of course pressure. We already know that this is from here. We can P of V can be written as PAVA gamma multiplied by V to the power minus gamma. Okay, so how does that work? So PV gamma is PAVA. So we're assuming we know the starting point, PAVA gamma. And therefore pressure can be written as PAVA, which is a constant. Yeah, so that's a constant multiplied by V to the power minus gamma. And this is the variable. So that's how we can do it. PV dV. So that's an integral. So work is equal to the integral from VA to VB of PAVA gamma multiplied by V to the power minus gamma dV. So that's PAVA. That's a constant, so we can take it out, multiplied by VA to VA, because VB is to VA, and V minus gamma dV. So we integrate. This is a gamma is a constant, so it's going to be PAVA multiplied by V to the power minus gamma plus 1 divided by minus gamma plus 1 between limits of VA and 2VA, PAVA multiplied by 2VA to the power minus gamma plus 1 divided by minus gamma plus 1. We can take the minus gamma plus 1 out. Minus gamma plus 1. And then minus VA to the power minus gamma plus 1. And since we know gamma, we can write PAVA divided by minus gamma is 5/3. So 1 minus 5/3, so minus 2/3. Minus 2/3. And this is 2VA to the power minus 2/3. Minus VA to the power minus 2/3. Is there anything we can do about it? Well, it's 3/2 minus 3/2 PAVA. And this is not really. Oh, we can take VA to the power minus 2/3 out, and we get 2 to the power minus 2/3 minus 1. And that is minus 3/2 PAVA to the power 1/3 multiplied by 2 to the power. Oh, it's going to be something. Cube root of 2. So plus 1 minus 1 over cube root of 4. That's the exact answer, but yeah. Okay, so that's the work done. That's the work done by the gas. Number 6. A heat engine operates on the cycle ABCD shown on a PV diagram. The working substance is a monatomic ideal gas. The pressures and volumes satisfy PB equals 4PA and VC equals 3VA. Okay, so determine the efficiency of the engine. So the efficiency would be the work done in a complete cycle divided by so the work done in a complete cycle divided by the work done on the gas. Wait a second. Okay, so for this PB is 4 PA. So this is P. This is PA, and this is 4 PA. And if this is VC, so that's 3V1. So this is 4P1, and this is 3P1. PVA isochloric increase of pressure, isobaric expansion, isobaric. Just a second. B to C, heat in, heat in. Yeah, okay, that makes sense. Efficiency, C, is the work done by the gas, done in one cycle, divided by the energy supplied, so heat supplied. That kind of makes sense. And the work done in one cycle is the area of this rectangle, because when the gas expands, it does work. And then when the gas is compressed, work is done on the gas. So compression, and contraction. Well, yes, contraction. And therefore, the work is the area, which is equal to P2 minus P1 multiplied by V2 minus V1. So it's the area of that rectangle. Or in other words, that is 4P1 minus P1 multiplied by V2, which is 3V1 minus V1, which is going to be 3P1 multiplied by 2V1, which is 6P1V1. Now, the heat supplied. So heat is supplied in uh, in the process AB, and it is supplied in the process BC. Heat is supplied in AB. So we need to understand what AB is. So AB is an isochoric heating, because we are heating the gas and the pressure increases, the volume doesn't change. BC BC is an, sorry, it's not a compression. What am I saying? It's vice versa. BC is an expansion, and this is a compression. And then isochoric heating, then BC is an adiabatic, isobaric expansion. CD is an isochoric cooling. So we're taking heat away from the system. And DA, that is an isobaric compression. Okay, now heat is supplied in the process AB because it's a heating. And now in BC, it's an isobaric expansion. Well, If the gas were allowed to expand, that means it is being heated as, as a baric expansion, because it's expanding, but the pressure remains constant. That means it is being heated in AB and in BC. Okay, so how much heat is supplied? Well, we know that at constant volume, heat supplied in process AB is the number of moles times CP. So CV is constant volume, and multiplied by the change in temperature. Yes, change in temperature. So in the process AB, it's N multiplied by CV multiplied by change in temperature, which is 3P1. And for a monatomic gas, do we know that it is a heat engine monatomic ideal gas? Okay. We know that for a monatomic gas, CV, I need to double check. CV monatomic. Monatomic gas, CV is 3/2 and CV is 5/2. Yes. CP. Monatomic CV is 3/2 and CP is 5/2. Yes. CV is 3/2 R and CP is 5/2 R. And that is N multiplied by 3/2 R multiplied by 3P1. So that is N times 9/2 RP1. N times RP1. The heat supplied in the process BC is the number of moles times Cp, because now it's at constant pressure, times the change in temperature. And sorry, I lost the. Did I lose the change in temperature? Oh, what am I doing? Sorry. Change in temperature, not pressure, of course. Okay. Now, we have PB, VB is equal to nRTB. And therefore, the pressure at point B, we know that it's 4 PA, and the volume at B is VA equals nRTB. So TB is 4 PA VA divided by nR, which means it's 4 TA. So the temperature at B is 4 times TA. Well, yes, it's delta T is 3. So 3 TA. And that is N multiplied by CV, which is 3/2 R multiplied by 3 TA. Now for BC, the temperature. So we need the temperature at C. So PC VC is equal to nRTC. So PC is going to be 3 times 4, it's 12. 12 PAVA equals nRTC. So TC is 12 TA. And so for BC, it's going to be N multiplied by 5 over 2 R multiplied by change in temperature. So it goes from 3 to 12. So the change is 9 TA. That's a significant increase in temperature, but anyways, that's N multiplied by, well, that's fine. Okay, so efficiency C is going to be work done in one cycle. So the work done is 6 PAVA divided by QAB. So it's N multiplied by 3 over 2 R times 3 TA plus N times 5 over 2 R times 9 TA. And we know that PAVA is NRTA. So it's 6 NRTA divided by, so that's what, 9 over 2 NRTA plus 45 over 2 NRTA. NRTA cancels. 6 over 45 plus 9, 54. 54 over 2, which is 27. Now, surprisingly, 2 over 9, which is approximately 22%. Wow, that's a lovely result. Energy supplied. Yeah, so that's quite typical of a heat engine. Having a heat engine with an efficiency of 22% is quite common. If you look at internal combustion engines, right, like an engine in a car, a typical efficiency is about 25%. Okay. So moving on. A Stirling engine operates between a hot reservoir and a cold reservoir, temperature Tc. A gas undergoes two isothermal and two isochoric processes between V1 and V2. Derive an expression for the efficiency of the engine in terms of Th and Tc. Let's see if we can do that. So Stirling engine. So we have PV, we have volume V1 and V2. And these are isochoric. So we have an isochoric heating. So we have two temperatures. We have T1 and T2. So these are isotherms. So these are lines of constant temperature, right? Because if you think about it, if PV equals nRT, if T is constant, that means PV is constant. And that means that P is inversely proportional to volume. So these are called isotherms. Therms. And now, so the process goes like this. So we heat up the gas. So let's call it A, B. Then it goes C, isothermal expansion. And then it goes isochoric cooling, and then isochoric cooling, and then so yes, that's a Stirling engine. CD. So let's describe. So AB is an isochoric heating. BC is an isothermic expansion. CD is an isochoric cooling, and DA is an isothermic compression. Okay, so we want to know the work done by the gas. We want to know the work done by the gas is that is the area. Okay. Work done by gas in one cycle. So the work done is equal to the work done in the process BC minus the work done in the process AD. And for the work done, work in the process BC is equal to the integral from V1 to V2 of P dV. But we know that pressure is nRT divided by V. So we can do that. So nR divided by nRT integral of 1 over V dV of V1 to V2, and that's nRT logarithm. So that's T2 logarithm T V2 over V1. Nice. Now the work done in the process AD is going to be negative because work is done on the gas. But we're just interested in the area, so we just need to integrate. Once again, I do V1 to V2, P dV, and similarly is going to be nRT1 logarithm V2 over V1. Okay. And then, so that's the total work done. So work done by gas is going to be N R logarithm V2 over V1, open bracket, T2 minus T1. Okay. And now the heat supplied to the gas. Heat supplied to the gas. Supplied to the gas. Well, heat supplied to the gas is supplied during the process AB. AB plus the heat. It is supplied in the Q heat is supplied in the isothermic expansion, right? Because if it's expanding but not cooling down, that means you're heating it up. QBC. But in the process of AB, in the process Q heat supply during the process of AB is equal to N, N C, it's a constant volume, CV times delta T, and in the process of which, so that's N, and because this is a monoatomic gas, and it's going to be CV, so that's 3/2 R multiplied by T2 minus T1. And heat supplied in the process of BC, well, for process BC, we can write the first law of thermodynamics. Heat supplied is equal to the work done by the gas in the process of BC plus change in internal energy. But change in internal energy is zero because the temperature doesn't change. And therefore, QBC is equal to the work BC, which we already know in the process of BC, the work is nRT2 logarithm V2 over V1. And now we can find the efficiency. Efficiency is equal to the work done by the gas, which is nR logarithm V2 over V1 T2 minus T1 divided by N 3/2 R T2 minus T1 plus nRT2 logarithm V2 over V1. And I don't think we're going to arrive to a expression containing only T1 and T2. I think we need to make further assumptions and says for the ideal Stirling cycle, the perfect regeneration, so the heat exchange during the isocause is internally reused. Well, okay, if the heat is internally reused, but that's not. Okay, so we can cancel the NR, and but we're still left with ln V2 over VR. So we, as long as if we don't know V2 and V1. Okay, let's make a wild assumption. The wild assumption is that the volume V2 is 2V1, assume. Okay, so that's going to be logarithm of 2. And that makes our life slightly easier. Logarithm of 2, T2 minus T1. And that's going to be 3/2 T2 minus T1 plus T2 logarithm 2. Okay, so yeah, let's keep it like that. All right, so that's the efficiency, and of course it's yes. Now, for a Stirling engine, for an ideal Stirling engine, is an engine where the heat that you supplied. So basically, how does a Stirling engine work, right? So if this is an engine, you go heat in, heat out, and then you do useful work. work. An ideal Stirling engine allows you to take this heat out and regenerate it and put it back in. And then you get more useful work. You get bigger efficiency. And in that case, the efficiency would equal to the Carnot efficiency. So Carnot efficiency is the maximum possible efficiency for a given temperature. So Carnot efficiency, C eta is 1 minus T cold over T hot. So that's the maximum possible efficiency of a heat engine. Okay, and I'll skip the next one. Sorry. We'll have to finish. Well, no, I won't be able to finish this, but try to do this. I'll give the answer. I'll post the solution here so you can look through. And I'll see you next week for some maths, and I'll see. Yes, you know how to access the board, right? I assume. Bye. Thank you.